Okay, let's see how could we draw the figure. This is my this is a freehand drawing of it, or let's say the harshest freehand drawing of it, but okay, no problem. Let's see how could we draw it. First off, this is a square, and on the centers D, C, A, and B, we draw a quarter of a circle, which radius is the DG. For instance, here is DG, and DG is the half of DC. Okay, so first we draw quarters of circles, which centers are DC, AB, and radiuses are half of the square side. Now, how could we draw these circles inscribed in the quarters, also the center circle? In order to draw a circle, we need two information. One is the center of it, and the second is the radius of it. Now, let's join this point W to the tangent point, the point of tangency, and let's call it as, say, as N. Okay, here we suppose that this is the true drawing, and we do some investigation to find the features of it. So we just connected W to the point of tangency. So since DA is tangent to the circle, then it should be 90 degrees. I proved that before. And this is a square. ABCD is a square, so these angles are 90 degrees also. So this is also 90 degrees. Now, here we got a line AD with two perpendiculars. And according to another theorem, we prove these two perpendiculars should be parallel. So that means NW is parallel to AB. Now, here we got two triangles. The first one is the little one, MWD, and the second one is DAB, which are similar because they got three equal angles. Here M equals to 90 degrees equals to A, and D, let's call it D1 and D1, the both of them got D1, and this angle W and B1 are also equal because these two are parallel, and another line intersect them, so these two are also equal. B1 equals to W. So the two triangles are similar. Okay, the relation is dn over dA, dn over dA equals to dW over dB equals to MW over AB. So MW, and let's show MW by R. Okay, the little r. And let's show the sides of the square by A. Okay, what was that? Okay, this is A, this is R, and this A. Now, here dW also equals to the radius of the quarter. Let's show that, which is the half of the side, okay, or A over 2, they have this radius minus the radius of the inscribed circle itself. So the W is A half minus R. So let's put it here. A half minus R, R minus 1. And dB, the diagonal by the Pythagoras theorem, now this is, I draw it here again, this is a DB triangle, and this is A also, and by the theorem dB squared equals to A squared again plus A squared, which is 2A squared. Then dB would be the square root of 2 times A. So we put it here, to A. Now here this times this, AR equals to this times this, A times A half minus R. So and this is from here we know we add both sides by AR. So the left side would be and the right side would be this, a square over 2. So from here R would be this. Okay, this is the radius of the inscribed circle, but where is its center? And the distance from its center, the distance of its center from D, as I mentioned before, which is dW, is the radius of the quarter, which is A half, minus the radius of the inscribed circle, minus R, which is this. Now you could easily calculate it. So we put one leg of so after identifying the point W, we could put one leg of our compass on W and draw the circle which radius is this, or or we could just put one leg of the compass on W and the another leg on the intersection between the quarter and the diagonal, and and with with that radius we draw the inscribed circle. So but what about the center circle? Its center is the center of the square, which is the intersection of diagonals. So from here to C is the half of the diagonal, or AC half, and is also equal to the radius of this, the center circle. Let's show that by the big R, plus from here to C, which is the radius of the quarter, which is this A half. So R would be, the center of that would be AC minus A half, and AC was the square root of 2A, or we could write it as A half times this.